lecture. This is part of a ECE Distinguished Visitors Program that he is visiting IISc. This is the first time he's visiting IISc in Bangalore, so let's welcome him. And so we would also like to thank the generous support of Ms. Nirmala Pulur, who was an alumni of ECE, who has made this visitors program possible as well. So just a quick introduction about Professor Yuri Kivshar. He's currently a faculty in the material physics department and heads the nonlinear physics group there at the Australian National University. He obtained his PhD in 1984 from Kharkov, Ukraine. He left the Soviet Union in 1989 and then moved to Australia in 1993, where he has been a faculty since then. He's very well known for his work in nonlinear physics, nonlinear photonics, and physics of metamaterials. His main contributions in these areas have resulted in many pioneering results in nonlinear localized modes in optical systems, optical solitons, vortices, and so on. He has many awards and fellowships for his credit. He's a fellow of the Australian Academy of Science since the year 2002. He's also a fellow of the Optica, or erstwhile Optical Society of America, American Physical Society, and also SPIE and Institute of Physics. He's also got many research awards to his credit. Lyle Medal, Lebdev Medal, the State Prize of Ukraine in Science and Technology, Harry Massey Medal, Humboldt Research Award, SPIE 2020 SPIE Motzi Award, 2022 Max Born Award from Optica, and more recently 2025 Zeiss Research Award from Germany as well. So with that introduction, I would like to welcome Professor Yuri Kivshar to give this lecture.
Thank you, Varun, for introduction. Thank you, everyone, for coming. I see some faces from my yesterday student lecture. That's good. But I apologize if you will see some similar slides. It can't avoid in the fall 2 seminar talk and 2 lectures which I'm given here. Anyway, today I try to do something more general and more specific, trying to overview the particular field. And you know, when I started to count these M's, I count Mie-5, you know, metamaterials, meta-optics, Mie-tronics, metaphotonics, and metasurfaces. Actually, I'm supposed to mention everything today. Are you sure I need that? I will stay here. Okay. Okay, I will not move that far, okay? Should be loud enough. Okay, so let's start. Assuming that there are some people who have no idea about what other faculty members here are doing in photonics, I just put the slide. What is light? It's a lot of manifestation of light, which you see in nature. Actually, it was much brighter here, but you understand where light comes from. But for scientists, light is actually presented like a part of electromagnetic radiation. So this is a visible part which we usually deal with, but in reality it's much, much broader. It's a span from between radio waves and X-rays and gamma rays, so you see that it's a very broad spectrum. But what is unique about that is that electromagnetic waves are very similar, and they are described by the same equations independently on wavelength. Of course, even properties and manifestation can be completely different. And the guy behind all this electromagnetic waves, of course, there are many different stories, but actually it's believed that, of course, equations are in this very simple form. Oh, sorry. So it's James Maxwell. This is his monument in Edinburgh, in the UK. So he suggested these equations, which basically present a very simplified version of what is currently called Maxwell equation, extended version. So it's important for me to start from Maxwell, because Maxwell equations cover all the spectrum and cover different types of waves. And actually, in particular, optics applications in photonics, we call optics usually when we are dealing with normal light, And these days we like to say photonics because we assume that we will go to the level of individual photons in quantum optics. And that's how photonics appears. I still need to learn how to use it. So there's a lot of optics application which you can imagine, and you can actually see many of them in your real life. So of course, communication now happening through optical fibers, not electric fibers. Then data storage based on optics, this fabrication, different type of machine processing, and amazing, of course, many of you get through that optics application in the medical application. So optics basically everywhere. So usually people say that our future totally will deviate from electrons to photons. That's what we try to believe, and we conceptually motivate our research. Of course, the main important things to move from free space optics, even people say about wireless communication, to some integration to so-called photonic chip. In Australia, we had, for 15 years, we had the Center of Excellence Kudos. Some of you may heard about that. Ben Eggleton, Australian scientist who spent some time in Bell Labs, was a director of the center. I was actually deputy director responsible for research topics. And that's what we try to put motivation for the center. The center actually aimed to move from expensive, power-consuming type of structures from yesterday to today, what we actually have in our current life, millimeter scale, centimeter scale, type of optical chips, to the future. Future, that's what already implemented in many applications, micrometer scale structures which use light for processing to match with optical fibers for long distance communication. And basically, this is what many scientists these days are working on. And Kudos was actually developing different applications for chip application, and spin-off of that Kudos activity now different centers, in particular centers working on optical comp and other type of applications based on optics. Okay, but if you go to smaller scales, this is not yet sufficient. So you need to have ability to to scale all these functionalities and devices, and that's how this new interesting field came, which is called nanophotonics. Nanophotonics dealing with the small objects, and where we actually should apply different ideas from to create small devices. And then for nanophotonics, you basically need something new, because simple scaling will not work. And here, actually, we come to the interesting concept which appeared completely in parallel to development of nanophotonics, so-called metamaterials. So meta, now people recognize meta through this name of social media, former Facebook, but meta itself actually comes from Greek, and it means beyond. And here it's, we use that meta to identify a new generation of type of structures, meta beyond normal materials. So it's a man-made materials which do not exist in nature. So of course there are different types of metamaterials these days: acoustic metamaterials, elastic metamaterials, but we are talking about electromagnetic metamaterials. So what is the idea of metamaterials? Why it's beyond materials? So normal materials have more or less this type of concept behind. So we have a like solid piece of material. We have no idea what is inside, but everything is so small that we don't see that. But in reality, everything consists of atoms and molecules. We are too small to touch. We can't actually feel them. We can investigate them through different type of interactions. For example, from just Bragg scattering to understand that it's really lattice inside composed of all these molecules. We are talking about solids. But this is what comes from nature. So what we are doing for metamaterials, we do something very similar. So we do some structures. This is actually a photo of real structure, one-dimensional structure fabricated in RMIT in Melbourne. It's an flexible substrate by Martin Mitchell group and during Kudos time. So basically the structure has a similar idea. So it's composed of very tiny elements. This is roughly shown here, just to define functionality. So we call them meta-atoms. We're much larger, of course, than atoms and the molecules here, but we're still much smaller than wavelength of light. So by touching by finger, you don't actually understand what's happening inside. And then basically some images of such structures from our research. I will mention them later in the talk, but this is to understand that what's happening. So it's different type of design of very small structures were manufactured due to modern applications of nanotechnology and nanofabrication facilities, which also exist here. To my great surprise, sorry guys, I need to learn how to do it very smooth. But so that's the idea of metamaterials. So we create structures. Why we do that? We basically try to introduce properties which do not exist in nature. I don't have time to explain many of these properties. I will explain few of them, but just to clarify more what we do for electromagnetic material. Electromagnetic material, actually, electromagnetic waves are composed of two actually components, electric and magnetic. So there are two fields, electric and magnetic, together create a structure of electromagnetic waves. So we need to learn how to control electric and magnetic component of the wave. For that, we introduce resonators. This is the simplest resonator which will interact with electric component. This is metallic rod which allows to create electric dipole resonance by separating electrons inside by illumination of electromagnetic waves, and it will allow you to control electric component. In addition to that, we need to learn how to control magnetic component. Usually we are dealing with non-magnetic materials, so it's not a real magnet which has a magnetic nature from the structure, but we create structures which allows you to actually introduce magnetic moment. This is the first in this field structure suggested by Sir John Pentry, so it's so-called split ring resonator, metallic ring with a cut. If I apply electromagnetic radiation, we excite free electrons inside of this metallic part. Free electrons will be oscillating, and we will create magnetic moment here. So it's what we call elementary unit of magnetic field, magnetic atom. So if we made a structure built of both these elements, we will be able to control actually properties of electromagnetic waves. More importantly, we actually may mimic different natural materials which are characterized by mu and epsilon in the Maxwell equation. And then basically to create values which do not exist in nature. So common materials are here, but by changing the properties of these structures, we can actually place material there and even create mu magnetic response by introducing these resonators. More interesting that we can go to the field of so-called negative refraction. So usually in the old textbook, when people consider something like Snell's law, refraction is assumed to be positive. That's why negative refraction word even does not appear there. But this is example of negative refraction. So if I have a source here, I bend light in a different way. So normal material should be bent that way, but backward, and then create one focusing point and one focusing point. This is usually called Vasilago lens, because Vasilago is a Russian scientist who was discussing properties of this negative index materials and metamaterials. Everything started around 2000, so now roughly roughly 25 years since first papers appeared in that field. And in OPN, Optics Photonics News, magazine of Optical Society of America, Optica, just celebrated 20th anniversary of the discovery of metamaterials. I believe Nobel Prize will come, but probably to different people, because Veselago unfortunately passed away. So you see that structures is composed of rods and this split-in resonator, and that was the first structures which were created to actually demonstrate negative refraction and negative refractive index. Of course, there was a lot of hypes behind that. I just mentioned one hype. Invisibility clocking was attracted a lot of attention from media. You know, media is very dangerous to deal with, because we present everything in the way we want, and sometimes hiding reality and the basic physical properties. So that was more or less clear, because people try to hide objects like here, and for that we need to create like a shield where properties of materials will be changed. That can be achieved with materials which are changed in both electric and magnetic response to bend light in the opposite way, so using negative refraction. And that's how it was built by David Smith, one of the pioneers of this field, and actually tested at microwave. In Australia, of course, we were very much attracted to that research, and also doing different clocks, and attracting a lot of media, so it was many publications and during these years. And I think some of you may know my good friend Jagadish. I just found a photo with him. That was a way for me move from microwaves. We moved to nanofabrication, try to do something smaller with nanofabrication team of Jagadish group that time. And then it came to the point when we basically need to use these interesting properties for optics. That's how meta-optics term appeared, and that basically idea of meta-optics is just to get rid of all these structures based on metals. These are examples. Of course, people first try to downscale of the structures from microwave to optics, but they did not work very well, because these structures use metals. These are all metallic structures. Metals invisible, very lossy. Performance of these devices which people created was very, very low. But still, people tried to do it, but it was no revolution, because it was no idea to apply that due to very, very strong losses. These are some cartoons which show different type of 3D structures. This is more this 3D also fabricated structure, originally in Berkeley. But it's we need to get rid of metals. In terms of electric and magnetic resonances, of course, main idea was where to get this magnetic resonances, magnetic dipoles, but also electric dipoles based on plasmonics were not good for that purposes. Still, the word meta-optics was used for the first time in 2011, when we were writing review papers with the now retired Professor Emeritus Roxma Fedron from Sydney University, and he suggested us to add word meta-optics, which I later changed to metaphotonics. Basically, the idea was to actually describe some interesting novel properties in optics, or traditional optics, which are enriched by elements of metamaterials, of provided metamaterials. What kind of elements? This is actually magnetic response, which may actually excite in the structures, in structured media. But it was not clear where to get these meta-atoms useful for optics. Because if you look at what I presented, everything based on metals, dipoles metals, split-in resonator metals, so it's a lot of metals. Actually, as always in physics, not maybe always, but in most of the cases in physics, everything was already known for a long time, and it was sitting there waiting when it will be discovered. Even topological photonics too, but people did not measure topological charge in all this band crossing. Anyway, that's actually here it's even more dramatic, because everything was in a paper by 1908, by Mie, who solved Maxwell equation, which I shown you previously exactly. For very simple system, it's a sphere, and you have plane waves scattered by sphere, and then he basically calculated without Mathematica scattering fields and wrote. You see that it's only schematic crocodiles, but you need to put every coefficient there. So basically, expressions for electric and magnetic field of scattering field from sphere. So what is interesting, if you look at his solution, you actually find that he also solution describe resonances. The resonances like that. The resonances, this is electric dipole, the slowest resonances, electric dipole and magnetic dipole resonances. So basically it happens when your sphere get light illuminated on that, and then light inside of the material sphere becomes lambda divided by n, refractive index, so it shrinks if refractive index larger. So and then geometric size of the sphere become comparable to your lambda over n. It's a typically geometric resonance. And it was there. So in this geometric resonance allows you to excite in a sphere both electric dipole and magnetic dipole, very similar what is required for metamaterials. So basically we may switch from metallic lossy structures in optics, which are not useful, to dielectrics. And that was kind of a very big jump in research. And that became to so-called Mie-resonant photonics, because first of all, we need resonances. This word appeared in a conference in ISMAT, very famous conference in Singapore in 19, when editor of photonics research was taking an interview. It was a session fully devoted to that. And then we discussed with Mark Brongesma, and he basically somehow mentioned that word Mie-tronics. So basically this Rachel Won, who editor of Nature Photonics, liked that very much and put editorial, and somehow it came through, and then basically become already in a title and abstract of several hundred papers. Basically, all the structures which are drawn here allows you to draw different, or to bring different functionalities through these Mie resonances. So we somehow related to this elementary particle, which is here as Mie sphere. It excites resonance, and this resonance, because Mie sphere may support both electric and magnetic resonance, may be useful for different type of application. Okay, what kind of okay. What type of applications? There are many, but my seminar is very short, so I mentioned something what people here are interested in. We are interested in metasurfaces. First of all, metasurfaces, sometimes people call two-dimensional metamaterials. It's absolutely wrong, because in metamaterials, people look at average parameters in the three-dimensional media. In metasurfaces, we do everything on the surface, but we are not interested by average parameters, and usually it's normal propagation. Why metasurfaces got so much attention? If you look at number of people who publish metasurfaces, it's still going exponentially. Why? Because basically we observe revolution in optics. Why? Because usual optical elements produced by special manufacturing units were basically lenses, concave or convex lenses, and lenses in your glasses. So you're dealing with lenses every day. The most, of course, with glasses is not that critical, but if you imagine different type of devices with a very huge resolution, which Canon, for example, produce, these are huge objectives with many lenses, specifically engineered, the huge bulky structures. But what we can do with metasurfaces, we can actually reduce all these bulky structures to very thin layer. What is important, we put some elements there and we engineer these elements to achieve different functionalities. What is interesting, that for example, usual lens, of course we can do it with a lot of optics, well, the usual lens is still, in the best, it's a millimeters thick. And basically it has prescribed shape here. So what this revolution suggests, we shrink it to several hundred nanometers by structuring the surface in particular way, we achieve the same functionalities. Of course, aberration, everything. Of course, people dealing with that, so don't ask me tough questions. So of course, it's not that easy. And basically what we have, instead of that conventional lenses, we have something structured. This is the image, SEM image of that structuring. And that there are 22 companies working with metamaterials, already 3 or 4 companies, which actually produced something what is related to meta lenses. The most famous meta lens from Federico Capasso and from Harvard. So why it's interesting? First of all, it's thin. Second, we can actually tune the structure by, for example, using phase change materials or liquid crystals, a lot of different ways people talking how to tune properties of materials, which is absolutely impossible here. And then if you reduce, if you get few stacking of them, you can completely change functionalities and type of functionalities. So metasurfaces explode. I believe almost everybody heard that, but it's actually exploded in different directions. So this is in a few years ago with my colleagues from Singapore, we put that perspective and we identify a few most recent, at that time, a few years ago, directions in metasurface research. So it was biomedical applications for sensing, hybridization with two-dimensional materials because they're all flat, then some quantum applications with, for example, multiple generation of SPDC or this tomography, quantum tomography, and also communication information metasurfaces. Believe me, people from this community do not talk to people of this community. It's so big already, and I'm not sure how often you talk to people from Arseny group in Singapore, but you were doing very similar things, but you're in terahertz, and then Mano was working in terahertz and Arseny was working in optics, but it's still different, different functionalities, you know. Anyway, it's very hard to actually understand all these metasurfaces, metasurface research, so many of them. But some smart people suggested that we can divide them in roughly in 2 big groups, which makes sense. Of course, in reality, there are something in between. But this make rough ideas what we are doing in this research. So first of all, it's metasurfaces with local response and metasurfaces with non-local response. So what is the idea? So in the local response metasurfaces, we have all these elements. And these elements we engineer at will, for example, from Mie resonances or for something else. I will not reveal you everything. And then in non-local metasurfaces, we are talking to each other, so we take advantage of non-local resonances. So resonance is similar to in photonic crystals, which involve Bragg scattering, so it's extended resonances. This is 1 unit resonances. And that somehow may classify them and engineer. I give you a few examples. This is fabrication, I will show you. This is non-local metasurfaces. And of course, non-local can be with low refractive index because we don't need to support Mie resonances. Here, units should be with high refractive index, and we need support local resonances. Okay, I give you a few examples of each. So this is from recent work. So we use vanadium dioxide is known like phase change materials. So what we did, we put silicon nanopillars which support Mie resonances on a layer of vanadium dioxide on a glass. So basically, it has some phase sensitive material underneath, but all the resonant properties come from silicon. If you look at the transmission, so we were interested in transmission in insulating and conductance shape, because it's a phase change material which changes the structure at this temperature. We were looking at these properties. Of course, these properties are very different if you switch to from conducting to insulated phase. But we tried to trick that transition with light. That was quite unique at the time. Now there are several demonstrations already with delay publication. So with incident light, because light hit actually material and may go through these transitions with VO2. And this from changing magnetoelectric coupling in resonators. This is our metasurface. You see that it's a perfectly square lattice with these elements, but again, functionality comes from units, not from surface. Surface is just big for measurements, for everything. And this is concept. So in one way, because we don't change properties, and then another way we hit particular VO2 and then we change transmission properties, we see that very strong high hysteresis. Functionalities come from units. Everything happens from CV radiation, continuum wave for relatively low frequencies, power. So it's very functional piece of device, which is based on, again, individual resonances. Example of other resonances. This is a table which we made some few years ago. This is all resonances which you classified. You see that there is individual unit resonances, surface plasmon polaritons, hybrid states of electrons and electromagnetic radiation at the surface. The Mie resonances is similar for dielectric. This is for metals. And then when we put them in a structure, we basically create what we call metasurfaces or periodic structures of resonators. And as you see, that can exist in plasmonics and dielectric as well. So this is examples of what was fabricated. I will talk about plasmonic later, but we still continue with dielectrics. So how to get actually extended resonances? Extended resonances, there are different types of extended resonances, but one that attracted a lot of attention is so-called bound states in a continuum. What is this and how to actually deal with that? Actually, everything started in 1929. A lot of history here from pioneers of quantum mechanics, von Neumann and Wigner, who published this very short paper when we solved Schrödinger equation in 3D exactly. We found very funny solution, which I show here in drawing in 1D. It's a schematic what we found, because repeating that solution does not have sense, because I'm not sure we understood what we actually found. So this is from quantum mechanics textbooks. Usually you separate all states in quantum mechanics for propagating and continuum and discrete. Discrete are characterized by discrete eigenvalues, energy values which support these localized states. But bound state in a continuum appears in more complicated potential, particularly that's potential mimic paper by von Neumann and Wigner. So it's a sinusoidally decaying tails of this potential. And then inside, below the maximum and above epsilon 0, where localized states exist, you can construct, and we found this exactly solution exactly, fully localized states, absolutely localized states, but it sits in a continuum. It sits in a continuum spectrum. So why we are interested in these states? Of course, we can always have a guided mode fully localized, propagating and carrying light. But this type of states, they coexist with radiative states. So basically, if I slightly release these conditions, I will able to talk to them through radiation, pump them, or actually get some information to them, but I still can have a light sitting and localizing for a very long time in this state. That was somehow missed for a long time. People did not realize why we need it, but it was a lot of fun to reproduce that. But in terms of metasurfaces, the states appeared in a very simple setting. We actually published a paper after I visited group at Rajan Singh and got 2 more examples. So I was collecting examples. I had already 3 or 4. And suddenly, after visiting Rajan Singh and in Singapore, I got 2 more examples. And actually, my picture was suddenly completed. So basically, you see that what is the idea? You have a metasurface. If a metasurface is composed of symmetric atoms, you propagate light normally. And that mode is a perfect bound state in a continuum, which is also dark mode. So dark mode does not couple with mode in the lattice. If I break symmetry of these elements, I allow radiative channel to couple to modes on the structure. And basically breaking channels, and this is a different example. This is from Rajan group, right? Different example of these units which with symmetry breaking, which allows you to actually couple normally propagating radiation to metasurfaces and create this very sharp feature which is associated with strong resonance. So the state exists in a continuum, but to deal with that, we need to change conditions of full localization to actually access that state resonantly. And that's make a very big deal in terms of application. I will show a few of them. Okay, of course, in that state, we need to have a possibility to fabricate structures very, very carefully. And then very soon, people started to fabricate structures. You see that this whole structures has a broken symmetry in the lattice, different type of broken symmetry, but we all support very sharp resonances. And of course, this resonance is actually controlled by these asymmetry parameters, different type of asymmetry parameters. I don't have time to discuss what was happening for several years, but I just will mention few applications to give you some appreciation what we are doing. This is an example of application of metasurface with resonances for biosensing. So we fabricated 10 by 10 pixels. So each pixel is metasurface, composed of two tilted bars and made of silicon. And then each pixel produces resonance. Here you see that peak is a resonance coming from this pixel. And because we have scaling here and scaling there, we produce 100 peaks. Up, too early. If you produce 100 peaks, we are slightly separated. Of course, it's important what kind of Q factor, so localization it is. But by coincidence, we had a good Q factor, 150, I guess. So we did not, we needed enough 100 peaks to actually do the sensing. So sensing is provided here in different ways. So when it's the following way. So you have an analyte, some substance we want to feel. We just launch it on that metasurface, and it changes the shape of these resonances because internal oscillations of these materials will interact differently with different type of resonances. And then how you can see it, you can map it on 2D barcode and measure it in a very simple experiment without any special spectrometer. So these measurements will give you barcode. Barcode can be used as a library to characterize different substances and basically how the sensing appears. Of course, this is first and very primitive. It was later on, it was a hyperspectral approach, and it was highlighted in OPN as a feature story of 2018. Very recently, just a few weeks ago, we actually employ both local and non-local responses to create so-called meta lenses in collaboration with HIT group in China. So basically here is the following structure. So we have a periodic lattice of a very fine disk, which create extended non-local resonance, and we tune phase inside by making this small hole and varying its position. So this position allows you actually to shape your lasing beam, so we can generate from that metasurface a lasing beam, not only Gaussian type of distribution, but any type of distribution you want. So basically, you don't need a complicated device. You just generate that beam exactly from single metasurfaces, of course, with a gain imposed that. People believe that bound states in a continuum are only associated with dielectrics, but it's not true, because bound states in a continuum are general wave phenomenon, so it should appear in any type of wave problems. And of course, people know them in acoustics and different type of wave type of propagation, where you find some interesting structures with usually called dark modes. This is example of our very relatively old work with Baohua Jia from that time from Swinburne University. She got a very bright students who fabricated structures. It's these pillars covered by very thin layers of gold. So it's a plasmonic, but it's a relatively small plasmonic. And then he basically observed very sharp resonances. This is another work from Germany. You see that peaks, and we observe high order quality factor. And then we finally understood what is happening, because from all metasurfaces you have a radiative Q factor and the dissipative Q factor. And in dielectrics, dissipative Q factor is small, and we basically control radiative Q factor. In plasmonics, we try to control dissipative Q factor. And this can be done through so-called engineering of local and non-local response by playing with height and distances. That was theory was summarized here. Again, the same student who was a student in my group for 1 year. No, postdoc for 1 year. And they see that this dissipative Q factor also follows some interesting laws, and this is examples. And you see, theoretically, you can achieve very high for nanophotonics Q factor. 150 is relatively very large, and we can do a lot of things for sensing and for other applications. Okay, I'm moving ahead, and I come to chiral metasurfaces. I will talk more tomorrow and my tutorial lecture, but here just few snapshots why we got interested. First of all, again, history. History comes from Lord Kelvin, who introduced chirality. This is his definition and picture, which appears in all books and review papers on chirality. And basically, chirality described by circular dichroism, optical activity, but here it's a very simple expression. And then it was a lot of effort in plasmonic, because plasmonic concentrate energy, and we try to enhance chirality. Why? Because natural chirality is very weak. If you want to do something in chemistry or on chiral sensing, you need to have much bigger values of chirality. And that's in plasmonics. If you see structures, we try to expand because it's very thin structures. And then different type of structures, we measure it. And this is a nice review paper. That time was a pioneered group of Harald Gissen and Na Liu, who is now editor of Science Advances. And we push a lot of plasmonic. So when we started to do that, one of the first questions was, can we achieve maximum chirality? Because these people talk about enhancement, but it's still 20%, 40%. But if we can achieve maximum chirality, actually, term maximum chirality appeared in this blue sky research from Germany, but we try to actually understand if we can actually do that. So what exactly we want to do? You propagate left and right polarized light on a structure, and then we see either completely absorb one polarization or completely transmitted, reflected one polarization. So basically, if I do the difference, so I will see just maximum chirality effect. That was never, ever actually predicted or even discussed, and it was not clear how to achieve it. But we know magic word, bound state in a continuum. Actually, bound state in a continuum allows to do that. And with bound state in a continuum, we came with a theory paper. Of course, most of the research we come from theory paper, where we actually predicted that, of course, by adding some losses and doing this loss matching, it's very important in this type of problems because we don't have a phase matching here. We suggested the following structure. It's a C4 symmetry structure composed of rods very similar to this tilted rods which I mentioned for sensing, but they are vertically shifted, so they actually introduce shift vertically. Why vertically? It's basically, our idea was simple. We thought about plasmonics. We need to introduce symmetry breaking vertically, and that's how basically it came out. But in theory, we observe 100% transmission. You see that compare these two curves very close to 100%, so it was a maximum chirality mentioned. It was highlighted by PRL for physics. But you should understand that when you hear the word flat optics, you should not understand it literally. Metasurfaces are not flat. Flat means flat, but they are thick, because in reality, optics need phase. Phase can't be accumulated in a zero thickness structures. We need finer thickness. How thick? It's at least quarter of wavelength or higher. That's how people actually achieve maximum transparency. I will talk in tomorrow's tutorial how to actually play to achieve highest possible transparency and make it broadband. For single frequency, of course, we should use something like Kercher effect for compensation of reflection. But if we have already thickness in dielectric structure, that thickness does not require you to break vertical symmetry like we did with shifting resonators. We can play inside of this thickness. And this is an amazing story because everything comes like a discovery because and this is also discovery. We start from simple structure which support bound state in a continuum with a gamma point, periodic structure. Then, of course, we can't see it because it's really bound state, a dark mode. To make it, to open it, we basically tilt them. We tilt them. And then to introduce chirality, so what we should do, this is tilted in a plane, resonators, and this is how we fabricate it. And then to introduce chirality, the only what we need to incline them in the thicknesses of that metasurface. It's so simple, and it was not easy to fabricate, but still we can do it. You know, you can tilt your metasurface into EBL. And then what happens if I tilt them for those slantic resonators? Basically, these two C points, which appears after breaking symmetry in plane, were basically shifted. So one C point coincides now with gamma point. So there is a selected chirality or selected secular polarizations, which allows you to link with normally propagating wave. And that fabrication was done, as mentioned, as HAT. And we, of course, play with different structures and observed chiral emission based on these tilted structures, and also look at and membrane tilted, and also observe some what we call intrinsic chirality. But I think after that, what we demonstrated is the word extrinsic chirality does not have any sense because it can't be related to chiral lasing. Few more slides to show you power of these metasurfaces and different directions we may go. This was actually discovered by my PhD student who is currently in my group. So we were doing a lot of things, and in particular chirality, and then he came to me once and said, Yuri, I look at Wikipedia. You know that symmetries are defined as so-called Bravais lattices, and there are 14 symmetric Bravais lattices in 3D. But do you know how Bravais lattices on a plane? I had no idea, because all crystalline theory I was learning from 3D because it's crystalline. It's a very few which was two-dimensional. Now two-dimensional materials, of course, inspire a lot of thinking in the plane. But in fact, there are only 5 symmetry lattices or Bravais symmetries on the plane. And these are all 5. I think it's even from Wikipedia. So there is some, of course, we use square, or tetragonal, hexagonal, but there is a very simple monoclinic one. Monoclinic, actually asymmetric. It does not have symmetries in a plane. So may be useful for chirality. So what we do, we take monoclinic lattice created by absolutely symmetric elements, place it on a surface break vertical symmetry. I will discuss it tomorrow. I do a lot of advertising for tomorrow's student talk. And then what we can do, we tilt that, tilt and break symmetry in plane, and maybe this lattice becomes chiral. And you see that absolutely spherical elements. Of course, chirality is not big, but still it's non-zero. And then we made measurements. This is model theory, which show you how important to actually break symmetry. And this is measurements of chirality. It's not huge, but it appears exactly at resonances. I forgot to say that majority of the studies are deeply associated with resonances we can excite. This is exactly position of 2 resonances which show you this splash of circular dichroism. I think almost final slide, which I want to show, it's a very recent work which we try to actually understand how to modify metasurfaces to map them to properties of waveguides. In the theory of microresonators, not microwave, microresonances, there is known this concept of CROW, coupled resonator optical waveguides. Many people know that it was introduced by very famous scientist Amnon Yarif, was pushing him for different type of application, including including photonic crystal waveguide. So what we suggested recently, they just published yesterday in Advanced Photonics with a group of Zhanghua Han who did experiment. We basically suggested that concept of weakly interacting waveguides of different form. So we need weakly interacting waveguides which create kind of bound state in a continuum. Then we modulate them to open channel of radiation. Then it can be different type of structures, but with a very different dimensions. And we observe so-called flat band, because in reality, if you try to separate these resonators, basically you will not see any dispersion, so because it will link to frequency. But here, when you separate them, you clearly see transformation to flat band, and then you can offer different type of structures. For that, in even structures which this one, which support chiral band, is very similar to what I mentioned. Monoclinic lattice is a typical monoclinic lattice, but composed of this modulated waveguide, shifted to create this monoclinic symmetry. Anyway, I know that some people say, okay, this is blue sky research, where is application, we want to use it tomorrow. Just few snapshots of application, which some of them I mentioned yesterday. So metamaterials can be used for different things. So one of them, to reduce reflection, absorption of stacking in a solar panel. This looks like unusual, but it is company in Germany which actually provides this service. It saves you a lot of a few percent in that business, make a lot of money. Then this is new type of screening security in airport. When you don't need to stay in security, it will be search and go. The company before COVID was very successful. This is prototype. Company evolved. And my former student was employed there. Then different type of, stealth, all the technology basically based on metamaterials, because people did not tell you that, but initially that we basically created like a mushroom antennas, and that basically metamaterials which control both electric and magnetic scattering. MRI may be enhanced by different type of application of patches to enhance signal. That was, we also work on that now, company in UK, very recent developments. We can use iPhone for sensing or for creating holograms and images, and that can be already installed in your iPhone. But problem is, of course, cost. So I come to the end, basically saying that there are many interesting activities. If you were not familiar with that, you can look at literature and think how you can apply in your research this meta concept. So metamaterial appeared about 25 years ago as a basic concept, a lot of excitement and hype. Then basically we transform in what we call now meta-optics, with application to optics and metaphotonics. There are a lot of quantum activities, somehow second wave of quantum activities. Then I mentioned that after all, majority of all this effect are based on resonances. So when elements are very small, still reversing magnetic moment requires resonances. So we're all resonant, but you can basically hide resonances if you want to talk about average parameters. And then metasurfaces, it's very simple 2D. We're not 2D materials, but it's a related concept. We use magnetic response, electric response. This is, and flat optics, I mentioned you should understand with care, because dielectrics and metasurface. You remember I started my talk from Maxwell, and then I should finish with Maxwell, and that how to do it. In fact, what's happening, and when I was 50 years old, my group celebrated, and my former student, who is now Professor Ilya Shadrivo, he found this interesting site, which is academic journalology. And he put my name. Of course, he wanted to put his name, but he basically I cut him and basically demonstrate what happened before him. So it allows you to trace your supervisors through all these ages, and you can try for yourself. I think in India it will be maybe very interesting things. How many people come from Raman, for example, Panachatram. Anyway, my supervisor was Professor Kosevich. I mean, majority of these people already passed away. You should understand that. And he actually known as a very successful student of Ilya Lifshitz, and he contributed to book of Landau-Lifshitz. It's a different Lifshitz, Evgeny Lifshitz and Landau. It's a volume 7, Theory of Elasticity, and I actually started from the solid-state physics, and eventually came to solitons, and again, initially from solid-state physics. A supervisor of Kosevich was Ilya Lifshitz. It's not that one who co-author of Landau, it's his older brother. It's also many effects actually associated with family Lifshitz related to him, not his brother. And his supervisor was Landau. I think some of you know Landau. And Landau spent some time abroad, and then when he was doing a PhD under Niels Bohr. And he later, of course, was associated with Joffe in St. Petersburg, and then was not allowed like a pizza returned back to abroad. But anyway, he was supervised by Niels Bohr. Now we go up, and what we see, actually, we come to James Maxwell. So at some stage, I was doing solid-state physics, but destiny was such that I need to come back to electromagnetic theory and finish it with Maxwell. Thank you very much for your attention.
I have a very short question, because when you showed the bound states, is there a way to, thank you. Is there a way to sort of characterize the bound states in terms of whether the decay of the intensity is Gaussian or exponential? Is there a way to, why do you say it's a bound state and not a localized state, for example? No, but it is, but in which case, would you... Yeah.
I don't hear myself. Not just because it's a localized state, bound state.
Probably it's because of the history. Bound state in the continuum was, people called it bound back, and that's why, right? But it's a localized state.
Of course, it's localized states.
From electronic viewpoint, we usually make a distinction in which a bound state usually goes down as a Gaussian, for example, it decays, whereas a localized state decays exponentially. So is there a way that you can distinguish between these two scenarios here?
Is it very important for physics, Gaussian or exponential? No, it was a lot of maths theories about that, about different models to study how it happened, which happens. I think we have different laws of localization. That's not important. But they're localized states, yeah, definitely. Yeah, so it's just, you may use that name, yeah. Yeah. I don't think that it was used for a long time. I think that everything was refreshed with, I didn't mention here, with the photonic crystal community when we found the states in the membranes, the MIT group. Yeah. But it's, in some sense, it's of course localized states. Yeah. If you like it, you may call it like that. But instead of big, you should be some localized states. LS. Okay. It may be confusing because localized states used for many other things, It's disappointing. Nobody understood anything.
So we have a small memento for Professor Kivshar from ECE department as part of the...
If there's no other question, can I ask
please go.
Oh, okay.
Sorry. This is regarding the chirality of the wave function. And how much different the left and what's the maximum difference in the chirality that one can obtain in the present chiral structures between the left and the right circularly polarized
No,
lights?
here is maximum.
Fully 100%.
Nothing more than 100%.
Okay, right.
No. What is the problem with the chirality with plasmonic? Plasmonic has a very, of course, all approaches try to use enhancement. Enhancement in plasmonic near surfaces. So we basically try to do, we need to match it with the pitch of electromagnetic radiation. So we try to do spirals on some open structures, and then very hard to control actually how much you will enhance and what you will do. But still, I don't remember any demonstration of very huge chirality in plasmonic structures. But our point is that we don't need to do the time of games, of course, if you break vertical symmetry, it will be much easier to get chiral response, particularly in chiral structures. But if you don't break symmetry, thickness already sufficient. So currently, I didn't mention that, we are doing work when we have a membrane. Membrane is absolutely symmetric. But we break symmetry in a plane, 2D symmetry in a plane, and the structure becomes chiral. Why? Because we don't break vertical symmetry. Because in definition of chirality, you can have a right-to-right and right-to-left conversion. So it becomes chiral through cross-conversion. So this, in 2D broken symmetry, you can convert right to left, directly not converted to right. So it will be basically chiral through different mechanism and through modal structure, because it's thick enough to excite modes. Modes, again, resonances, modes, that's all in one basket, you know, because with no resonances, no modes, nothing will work. Particularly this modal structure, resonances, which I basically mentioned initially, very important. Yeah.
And also, are you, because you're using plasmonics, are you restricted to specific wavelengths here?
I'm not using plasmonic.
Okay, so,
People using plasmonic. okay.
so how well is the wavelength selectivity? Can one get the chiral behavior or the chiral separation over a broad range of wavelengths?
It depends on resonance. If the resonance is high Q, of course it will be narrow. But you can do broadband and still, it's a lot of game, you know. It's because, I mean, probably I didn't deliver the main message. It's like nature. We can engineer a lot of things at the level of single resonators and change something on the macroscopic level.
Talked about the maximum chirality, right? But that's basically in the 3D type of, with the thickness.
Yeah.
Right, with the thickness. But is it possible to achieve maximum chirality in 2D structure, what you were mentioning? In the 2D surface, like basically.
Yeah.
Can you, is it theoretically possible as well in?
Tomorrow. Tomorrow. I have examples. Yeah. No. Because I mentioned that if I break vertical symmetry, I can have conversion, for example, right to right. But if I don't break vertical symmetry, there is another part of this definition, right to left. So I will still have a cross conversion chirality. You know, it depends what you want to apply. You know, if you want to apply for chiral lensing, so what? You know, you can. Important to have chiral modes, and that chiral modes exist in both cases. Yeah.
So I had a question. So I think long back you showed slides about flat lenses. There were some patterns, I think about 100 nanometers to focus light. So I wanted to know if those patterns are like made mathematically or are they generated pseudorandomly, like Turing patterns?
Which pattern?
I think, can you go back to some slides?
Okay. That's a long story.
Maybe
Around
discuss during the coffee break.
Okay, sir.
Let's talk after that, because I will be searching for that. Okay, but, you not understand which you're talking about pattern. Yeah.
Hello. Yeah, thanks, Yuri, for a great talk. So just a general question. Do you have any thoughts on configurable metasurfaces where you can...
We call it tunable.
Tunable metasurfaces,
Yeah.
exactly. So where you can, depending on the particular modulation or particular application, so because the metasurfaces you showed today are created and then they cannot be changed.
No, that's a great question. So many groups are working on that. There are different ways. There are even review papers which discuss different ways of tunability. what we did in the past, we tried several approaches. One was based on liquid crystals. Liquid crystals basically can change orientation of molecules and change transmission. That was an old story, but then it was dramatically improved by Arseny from A-Star. I'm not sure you remember, but we put this control on each pixel of bigger metal lens, and they're fully controllable metal lens. But there are different other ways. For example, use phase-sensitive materials. It's a big business. People trying to do that. Yeah. Terahertz, yeah, sure. Terahertz, guys, much easier to do. In optics, it's much harder to do it. Yeah.
Just related to that question, I'm just very basic familiarity with computational materials engineering. I just have that knowledge. Now, similar to like how materials are designed, for a process leads to a structure, structure leads to a property, property leads to a performance. In computational material engineering, this is a sequence. Now, similar to that, are there engineering approaches to design metasurfaces in this sequence list: process, structure, property, performance?
Very good question, but it requires very long answer. Each group has different tricks. We come from physics.
Yes.
If you have time, please come tomorrow. I will discuss actually how to achieve maximum transparency, and how to achieve it broadband. Special tricks. But to that question, I asked once Federico Capasso, who is considered to be father of metasurfaces. Asked Federico, how do you optimize your metasurfaces? He said, I have 4 excellent Chinese postdocs. This is not way we like, because we do a lot of routine calculations. Unfortunately, by now, it's a lot of calculations. So we came from physics, but we didn't push it far because we're interested mainly in new physical effect. But in the companies, particularly in company A-Star, in Kuznetsov group and other groups, you don't fight for numbers, because you don't sell anything. But metal lens, this A-Star, when they're selling products based on the surface, is a very hard routine calculation work, a lot of calculations, because it requires adjusting many parameters, particularly if you want to achieve some improved characteristics like aberration-free type of metal lenses. Of course, Of course, people use adverse design, and of course, all the tricks, AI, whatever, everything. We also use it for a few times, but for specific designs. Yeah. Very good question. Yeah. Not resolved.
Other questions? Okay, if not, we have a small gift for Professor Kivshar from the ECE department for giving this talk as part of the ECE Distinguished Visitors Program. So I request Professor Vinay. We have 2 more lectures. Like tomorrow there is a tutorial, and then on Thursday we have a department lecture in IAP on chirality and nonlinear optics. So do attend that, and we also have a student interaction session after the lecture in IAP, Thursday at 4 p.m. So do attend that, and do avail the opportunity. Thank you very much.
Thank you for coming.
We also have a high tea in the other area.